second lecture of cloud computing. In this video, we'll be covering the second module, that is virtualization. We'll be discussing about all the important topics from exam perspective. And if you're new to my channel, do subscribe to my channel so that you don't miss out any of the updates related to cloud computing subject and other subjects also. So let's get started. First question which they'll ask generally is define virtualization and what are the factors that drive to virtualization adoption. So, understanding the definition, virtualization refers to technologies or methods which are used to create an abstract environment. So, we are creating this abstract environment such that this abstract environment will have many servers. These servers will comprise of multiple processors. There will be the RAM, ROM, and memory. So, by making use of a hypervisor, that is virtual machine manager, it will feed the software. This is hypervisor is a software which will feed in this particular machine, in this particular server, and from this server we can access the virtual machine. So this is how the entire virtualization actually works. Sorry, let's understand the definition first. So virtualization refers to the technologies or methods which are used to create abstract environment which will allow multiple devices to run on a same shared physical infrastructure. So we are sharing a same server here, but then multiple operations, multiple users are using it. That's what we can call it as a virtualization. So virtualization enables a program to emulate a special environment for running applications which are distinct from the host environment, thereby enhancing the resource utilization, flexibility, and security aspect. So, for example, we can take a virtual machine which is running on OS, Windows OS, which has Windows OS, but it is running on the Linux system. So, this is one of the basic examples which we must have encountered in our laptops or in our laboratories, right? Speaking about the importance, so virtualization will facilitate infrastructure as service in cloud computing. It will deliver the scalable and cost efficient systems. Along with that, it will also enable multiple virtualization types, which will include the storage, memory, networking, and others. Let's look into what are the factors. So what were the factors which led to adoption of virtualization? Why did we come up with virtualization topic? So the first one is increased performance and computational capacity. That is, modern PCs and servers are highly powerful, but they are often underutilized. That is, they'll have high CPUs, high RAM, ROM, memory processing power and all. But then, are we using it to the fullest? That's a question mark. So these systems can efficiently host the virtual machines. They can efficiently host the virtual machine managers and virtual machines. So, for example, a supercomputer can run thousands of virtual machines without its performance degrading or without its performance affecting. Next, we have underutilization of hardware and software resources. So, we know current IT infrastructure operates below capacity. So, many resources like office PCs or lab PCs, they remain idle when they are not in the working hours. So, virtualization will make use of these PCs and they'll make sure that during this idle time, other tasks are being executed. Then we have lack of space. That is, enterprises will face the challenges in expanding their physical data centers, right? Because there is less space, and if you are expanding, also it is very costly, right? So physical data centers need space and cost. Thereby, virtualization will help the server consolidation, reducing the physical footprint. Thereby, here you can access the data, or here you can access the virtualization, the server, without worrying about the space. Next, we have environmental and energy efficiency. That is, we are speaking about the green initiative. So, if we are reducing the data centers, not building the data centers, that means we are saving the power, because data centers will consume a lot of power, right? So, if you are saving the power, thereby you are moving towards the green initiative. Then you have rising administrative costs. So, the cost for power, cooling, and all are very high, right? So, if you are moving towards virtualization, then all this is not required. Thereby you are cut downing the unnecessary costs here. So these are all the factors which led to adoption of virtualization. Next, we have components of virtualization. First one is guest. So guest refers to the system that will interact with the virtualized environment rather than talking to the physical hardware directly. So here we have the physical hardware, here we have the guest, and here we have the virtualized environment. So I'm talking to virtualized environment rather than talking to the hardware directly. So here it could be the operating system, or it could be any application that will run under the virtualized environment. So here the guest will operate within the virtualized environment layer, and it is created by using the virtualized technology. So guest, yeah, that was about guest. Next we have is host. So host is like the underlying underlying physical environment, that is hardware plus OS combination. It could be the physical system or it could be the hardware that runs the virtualization layer. Host is the physical environment, okay, so in which we can run our virtual environments. So these environments could be managed and they could be executed in host. Host will have the real physical resources like CPU, memory, it will provide networking and all of that. Next we have is virtualization layer. So virtualization layer will manage the virtual environment and it translates the operations between guest and the host. For example, the virtual machine managers like VMware, VirtualBox are the well-known examples of virtualization layer. So this layer, no, it will separate the guest system from the hardware, that is the host system. It will provide an illusion that each guest is running on the dedicated server. But is it running on the dedicated server? No. It is sharing the resources from the virtualized layer through the host. Okay. So that was about the virtualized layer. We have covered guest and we have covered host. Next we have virtualized image. So virtual image refers to the image of the guest system. So this could be OS and any other application. So this can be the virtual machine also that will contain the software stack. Then we have virtual hardware here. So virtual hardware will have all the hardware components, CPU, memory and all. Then we have physical hardware. Physical hardware is there here. Physical storage is there here. Physical networking is there in the host system. Virtual storage means virtually you are storing the data here, providing abstraction of storage resources that appear to be direct to the guest, but they are not direct. We are passing it through the virtualization layer, then passing it to the host further. Then you have software emulation here. Software emulation means you are running the software or you are uh, understanding the behavior of hardware and other systems. So this will allow the guest to interact with the virtualized environment as if they were interacting with the physical hardware directly. So this was about the virtualized storage. Then we have physical storage covered. That's it. So all these topics are covered. So if they ask in exam about the virtualization reference model, you should write these three components firstly and then explain with this diagram. Next we have applications of virtualization. So looking at the applications of virtualization, first one we have is hardware virtualization. So in hardware virtualization, virtual hardware will allow running the system images, that is it could be the OS or any applications independently of the host. For example, a virtual machine which is running on the VMware or VirtualBox. So they are independent about the host, right? They are just running on this platform. Then we have virtual storage. So it provides storage like virtual drives or cloud storage solutions. Next, we have virtual networking. So this is used to simulate the networking with the actual physical networking. For example, VPN will create an illusion that we are being a part of a remote network. But are we being a part of remote network? We are just accessing the same internet, right? But then yet creating VPN. So this is an example of virtual networking. Next, we have is characteristics of virtual environment. So this was asked in the sample paper also. So yes, so the first characteristic is increased security. So virtualization will create isolated environment which will be separated from the rest of the world. So by this we are protecting from harmful operations of the third party. Example here is sandbox environments which are present in the Java virtual machine. Tools used here are VirtualBox, VMware, Parallels, which will provide virtual environments with default separation from the host system. So here we have the users, here we have virtualization layer, here we have the host. So you can directly contact without worrying about the host here. Next we have is managed execution. So virtualization will support advanced features like sharing, aggregation, emulation, and isolation. So sharing means hosts physical resources are shared here. Aggregation means it combines different resources from multiple hosts and then you are using it together. Emulation means virtualizes the environment or devices which are not present in the host. So here you are emulating it. Isolation means you are keeping the guest activities separate from each other, thereby preventing any interference if it is happening and enhancing the stability here. So this figure speaks about the managed execution. So in performance tuning, we'll be adjusting the virtual resource allocation to meet the requirements. So next we have is migration. So in migration, we'll capture and move guest state from one state to another state. For example, the Zen hypervisor, which will enable the live migration to optimize the data center workloads. So we'll see how this Zen hypervisor actually works. Then we have third point is portability. In portability, we have hardware virtualization. So the guest environment can be moved and executed across different hosts. For example, migrating a VMware virtual machine between different servers. This is an example of hardware virtualization. Then we have programming level virtualization, where platforms like JVM or .NET allow applications to run on multiple systems without any recompilation process necessary. Then we have user flexibility. That is, it will enable users to carry and deploy their system environment wherever they find a compatible virtualization platform. So this was about the user flexibility. Next we have the advantages. First one is efficiency. It means virtualized environments will fully make use of the resources, right? Then we have cost effectiveness. That is, reduced physical hardware. We are saving power, thereby saving cost here. Then we have scalability. That is, we can make use of multiple users can access the resources and share the resources here in the virtualized environment. Flexibility means it will allow testing and running of different operating systems, different hardware configurations, applications without altering the actual host environment. So then we have security. Security means it will isolate the guest operations from the host operations, thereby minimizing any sort of risk which could happen. So this was about the advantages. Again, this could be asked in exam. It is very easy to explain, very simple topic. Next we have is taxonomy of virtualization. This is again important. This was asked in the sample paper. Taxonomy will provide a structured way to classify the various approaches which are used to emulate and manage the computing environments. Main categories here include execution, storage, and network. In execution, we have process and system level virtualization. We'll look into how execution virtualization works. So the purpose here is to emulate the execution, which are execution environments distinct from the host. For example, by making use of virtualization, virtual machines or runtime environments like JVM, .NET, or the hypervisors and all. So further, they support multiple programs to run concurrently. Then we have process level and system level as subpart. Process level means these techniques run on top of the existing operating system, which has full control over the hardware. So the virtualization layer will create an isolated environment for these applications, which will operate as if they have their own OS, but in reality they are working on top of the existing OS, that is process level. So example here could be Docker or LXC. These are the examples. Then we have the system level virtualization. In system level virtualization, it is directly implemented on the hardware and it does not require an existing operating system. So here example could be the VMware, Hyper-V, RKMV and others. Next we have is the so without these within these categories, different techniques provide different virtualization computing environments. We'll look into what these techniques are. First one is bare hardware virtualization or bare hardware virtualization, where guest operating system runs directly on the virtualized version of the hardware. The hypervisor will manage the virtualized machine. Then we have operating system resource virtualization. This will provide an isolated instance of OS resources for running multiple users environment on a single OS kernel. Then we have low level programming. In low level programming, a virtualized environment can be created to run the programs compiled against the abstract machine model. Example here is JVM. Then we have application level. In this, it will isolate the application level by creating the virtualized libraries from the server. So the services on which they are completely depending, and it will enable them to run on isolated environment. Next, moving further, we have the figure which will explain about the taxonomy of virtualization. So this figure is very simple to understand, right? So here we have execution environment. Execution environment could be further classified as process level and system level. In process level, we have emulation, high level virtualized machine and multi-programming. Then under system level, we have hardware assisted, full virtualization, para virtualization and partial virtualization. So how is it this done? How is it done? Through process level or system level. These are the techniques and these are the virtualization models which are used. Next we have is the machine reference model. So machine reference model will outline the relationship between various levels of abstraction in the computing from the hardware to the user level program. So it provides a structured way of how the virtualization techniques work within a computing stack, with the focus on isolating and managing execution environments. So these are the top, like this is the definition of machine reference model. So next we have key components. Under key components, we'll have hardware level, hardware layer and operating system layer. Along with that, we have application layer also. We'll look into these one by one. So first we have is hardware layer. So it is ISA, instruction set architecture. It is depicted as ISA, this part. So hardware layer will define the processor instruction, registers and memory and interrupt mechanism. So it is all related to the instruction set. So it will include the system ISA and user ISA also. Next we have ABI, that is operating system layer, application binary interface. This will serve as an interface between the application and the operating system. It will ensure that application portability across the systems are happening properly through the same ABI. Next we have is application layer. Here we have API, that is application programming interface. It will interact with the libraries and operating systems, and after that it will provide high level functionality and simplifies the application development by abstracting the low level complexity, that is covering up the low level complexities. So here if you look at the figure, we have hardware first. So hardware will refer to the physical resources, processors, CPU, memory and all of that. So hardware, the relation is both host and guest systems will ultimately rely on the physical hardware, but through different abstraction layers which are provided here. Then we have ISA here. ISA we have explained. So ISA is important because it will establish layer of or level of abstraction between the operating system and between the hardware here. After that we have the operating system here. Operating system is the software that will manage the hardware resources and provide service for different applications or different requirements. Then we have system calls here. System calls will define the what to do, which program to run, depending on the operating system to further request the services here. Services could be memory allocation to create a process, IO operations and all of that. We have libraries here. Libraries are collections of the pre-structured programs that will run on the system whenever we call those libraries. Mathematical operations, networking, all those libraries are there. Next we have API calls. API calls are the routines, protocols which are there. So this will help the application to communicate with the libraries or the operating system further. Applications are the end user programs which we will use further. So this is about the machine reference model. Security machine reference model will separate the instruction into two parts. That is, first one is called as privileged instruction, and then we have the non-privileged instructions. So privileged instructions are those instructions which are executed in the supervisor mode, and then we have non-privileged instructions which will execute in the user mode. So here we have privilege layers and security comprising of the ring model. So privilege layers, in privilege layers we have three layers as ring 0, ring 1 and ring 1, 2 and ring 3. So ring 0 will tell the ring 0 means it will have highest privilege level. So ring 0 will have highest privilege level. It is also called as kernel mode or supervisor mode. So like the code running in ring 0, no, it will have unrestricted access to all the system resources like hardware, software, everything. So this is where actually the operating system kernel also lives. Then we have ring 1. So ring 1 means it is slightly above ring, slightly lesser than ring 0. This is the middle privilege level. So in this ring 1 is a privilege mode where the device drivers, so or any other system level software that need to interact with the hardware, but it does not require full access to the system. So ring 1 will provide a safe layer between the user applications and the most critical part of operating system. Next we have ring 2. Ring 2 is slightly lesser than ring 1. This is less privilege mode. So ring 2 is a privilege mode, slightly more restricted than ring 1. It is not commonly used in the modern day applications, as most of the operating system assign device drivers to ring 1 itself. So ring 2 offers more control than the user mode, than the ring 3, and it is less frequent because new architectures and operating systems do not have ring 1 and do not separate ring 1 and ring 2. Next we have is third level. This is the least privilege. So ring 3 is the least privilege mode. It is also called as user mode. So most user applications and non-critical software will run in this particular ring. So this is how the security rings and privilege mode works. On this side we have about the kernel mode and supervisor mode. So here this is just the explanation of all that I have spoken here. So hypervisor runs on the supervisor mode, overseeing multiple virtual machines. So they will manage sensitive instructions that execute in ring 0 to ensure isolation and control over hardware resources. So hypervisors will execute in the ring 0. So modern ISAs like Intel VT and AMD Pacifica will redesign the sensitive instructions as privileged, enhancing the isolation and virtualization efficiency. So if If they are non-privileged instructions, then they are converted into the privileged instructions. Thereby, they can run in the higher rings. So that's what it means here. Moving further, we have hardware level virtualization. So hardware level virtualization is also called as system virtualization, because this will abstract the physical hardware, and it will create an isolated environment where the guest operating system can run as though they are running on the physical hardware, actual physical hardware. Components will include the guest, it will have a host, it will have a virtual machine, and it will have a hypervisor. Hypervisor means virtual machine manager. So hypervisor will manage the virtualization, and it will provide hardware abstraction and resource control. Now let's look into the type of hypervisors. So there are two types of hypervisors called as type 1 and type 2. Type 1 are the native hypervisors and type 2 are the hosted ones. So here in this figure we can explain it properly. So the left side we can say that they are the hosted virtual machines, and on the right side we have the native virtual machine. So this hosted virtual machine or hosted virtualization means we are running the virtual machines or hypervisors on top of the existing operating system. So this is the host operating system which is present here. So on top of that we are running the virtual machine here. So here like we are isolating the host from the operating system, and each virtualization machine here will operate its own operating system which is independent of the host operating system. So here VMM, that is virtualization machine manager, will rely on the host operating system for hardware access, but then it can introduce some overhead due to the extra layer which is present here between the hardware and the guest virtual machines. So this layer or this virtualization is commonly used in the desktop virtualization environment, like the VMware or VirtualBox or the workstation and all. So speaking of the advantages, these are very easy to set up, very easy to use, and they have already operating system here, right? So they are just using it. So they are preferred for testing and development purpose. But then disadvantages, overhead can happen here. Speaking of the right side, in right side we have the native virtual machine or bare metal virtualization, where the virtual machine manager VMM or the hypervisor is installed directly on the physical hardware. Here we have the physical hardware, and it is directly installed on the physical hardware without any underlying host operating system. So this is called as type 1 hypervisor. So here by this we are providing direct access firstly, and because we have no host here, so it will result in typically better performance and efficiency. So this model is used in enterprise data centers, and examples are the VMware workstation or the Oracle virtual box. Advantages, it will provide high performance because we are directly contacting the hardware, and disadvantages, it is very complex to set up. So this was about the virtualized hardware. So this was about the types of hypervisors. So here I have written down the explanation regarding it. So here we have the virtualization machine manager, design or hypervisor architecture. In hypervisor architecture, we have three parts. So first one we have is the dispatcher. So dispatcher means the entry point for virtualization machines instructions or routing them to appropriate modules. So here you will route the virtualization instructions, VM instructions to whichever model they belong to. Then you have allocator. Allocator will manage the system resources which are allocated to each virtual machine. Then you have interpreter. Interpreter will execute the privilege instructions via routines which are triggered by the traps here. Next, moving on further, we have this Goldberg and Popek criteria for virtualization. So under this, we have three theorems. In exam, they may or may not ask this theorem, but it is preferred to understand this. It is preferred to know this in prior. So it is very easy. So the criteria established by the Popek and Goldberg define the requirement for computer architecture to support efficient virtualization. So these two were the scientists who invented these three theorems, and they designed the requirements for computer architecture to support proper virtualization to happen. So these criteria are crucial for designing the virtualization machine managers or hypervisors and ensuring that guest operating system can run correctly without the need of virtualize within the provided virtualized environment. So we have equivalence, resource control, and efficiency here. Equivalence means the behavior of guest operating system under the virtualization machine manager should be identical to the behavior on its physical host. Then we have resource control, that is VMM must have full control over the virtualized resources. Efficiency means most of the machine instructions must execute directly on the hardware without VMM intervention. Here we have the first theorem. First theorem states conditions for constructing a virtual machine manager VMM. So for any conventional third generation computer, VMM may be constructed if the set of sensitive instruction for the computer is a subset of privileged instruction. So this instruction or this theorem will state that all instructions that modify the system's configuration should generate a trap in user mode, allowing them to be executed under the control of VMM. So this will allow the hypervisors to control the instructions that would reveal the presence of abstraction level while executing the rest of instructions without any intervention. So here we are telling that sensitive instruction must be a subset of privileged instruction. So this will allow trapping and hypervisor control to happen. In second theorem, we'll be speaking about the recursive virtualization. So here recursive virtualization is possible if hardware is virtualizable firstly, and it supports nested hypervisors. So those two are the main points here. Then we have the third theorem. Third theorem will tell about a hybrid virtual machine, HVM. Okay, so HVM can manage systems where user sensitive instruction will overlap with the privileged instructions, but this is less efficient, and because it has like increased instruction interpretation, it has less it has less efficiency. Moving on further, we have hardware assisted virtualization techniques. So under hardware assisted virtualization techniques, we have these many categories. So we have 1, 2, 3, and 4. So first one is hardware assisted virtualization. So this is a technique which uses specific hardware features like Intel VT or AMD V. So we have seen these previously, right? So we'll convert from the unprivileged instructions and to the privileged instructions. Thereby, these can directly contact with the operating system or the ring 0 instructions through these platforms or through these softwares. So to enhance the virtualization process. So these technologies will provide direct support to virtual machine managers or hypervisors to run the guest operating system in an isolated environment. We are improving the performance, we are reducing the reliance on the software based emulation. So this will have better efficiency and faster execution of virtual machines, especially when multiple operating systems or multiple guest operating systems are running concurrently. Next we have is full virtualization. In full virtualization, we'll allow a guest operating system to run in isolated environment using complete hardware emulation without the without requiring any modifications to the guest operating system. So this method will provide strong isolation security. But then there are certain limitations here. So that is when the guest operating system is attempting to execute a privileged instruction, there might be some challenges. In order to overcome these challenges, we have hardware assisted virtualization, which is often used in conjunction with the full virtualization. So full virtualization plus hardware assisted virtualization can overcome the issues when we are trying to execute the privileged instructions. So this will ensure more efficient and efficient management of virtual machines. Then we have para-virtualization. Para-virtualization means guest operating system is modified to work directly with the hypervisor for certain operations. It could be the IO operations, memory management, in order to improve the performance. So this technique will require access to the guest operating system's source code for modifying it, making it more suitable for open source systems. So this para virtualization will improve the performance by eliminating the need for full hardware emulation. Here it is partial. You're not using it completely. You're using it only for certain operations here. But then it limits compatibility to modify the guest operating systems. Example is Zen Hypervisor. We'll look into Zen Hypervisor further. Then we have partial virtualization. In partial virtualization, you are emulating only some parts of system hardware, thereby allowing only certain applications or processes to operate in the isolated environment. While the guest operating system may not require full emulation, that's why we go up with partial virtualization. So this technique is used in scenarios where complete isolation is not necessary. Example could be the address space virtualization, which will isolate the memory spaces for different users or applications in the time sharing systems which are offering efficient resource sharing. Then we have operating system level virtualization. This is a separate topic. So in OS level virtualization, multiple isolated user space instances are created within the same kernel, within the same OS kernel. So here each instance will behave like a separate environment. Thereby they'll enable concurrent execution of different applications or services within the isolated context. Unlike the hardware virtualization, there is no need of hypervisor here because operating system will itself manage the separation process and execution of the instructions here. This approach is efficient in scenarios where multiple applications will share the same operating system. For example, the free BSD jails, Solaris zones, or OpenVZ will provide resource isolation without the overhead of full virtualization. Next we have is programming language level virtualization. So this form of virtualization will allow the programs to be executed in the managed environment across different platforms and operating systems. So it will make use of a virtual machine to execute the bytecode which is generated from the program's source code. So this will enable us to run the program with a corresponding virtual machine. So here this virtual machine, it will simplify the deployment process and increase the portability, because the same bytecode can run across multiple systems without any modification required. So here the virtual machine will abstract the underlying hardware and typically uses either interpretation or just-in-time JIT compilation for execution. Java's platform and .NET frameworks are notable examples for programming language level virtualization. Then we have application level virtualization. So this technique will allow applications to run in environments that may not natively support all required the runtime features. For example, it could be the libraries or OS components. Rather than installing the applications directly on the host system, the application runs on isolated environment that provides necessary support, often using the partial file systems or library emulation. So this process may include the interpretation or binary translation to adopt the applications to the host system. So this level of this virtualization is lighter than the hardware virtualization, and it is effective for running incompatible or missing libraries. So it is seen in tools like Wine for running the window applications on Unix like systems. It will support specific environments and is mostly used for isolating individual applications without the need for full system emulation. There are other types of virtualization. In other types of virtualization, we have storage virtualization, network, desktop, and application server virtualization. Storage virtualization means it is a technique that will abstract the physical organization of storage hardware from its logical representation, thereby making it easy for users to access it, manage the data without worrying about the physical location. You're just storing it. You're just storing the data here. Often using technologies here are the storage area networks for network-based virtualization. Next, we have the network virtualization. In network virtualization, without the need of physical hardware, you're providing the networking facilities. It could be the virtual LANs, or it could be the VPNs which we are using, and all of that. Then we have desktop virtualization. In desktop virtualization, you're providing desktop-like environment for the applications to run. So you're allowing users to access their desktop remotely through client-server model. So this desktop environment is typically hosted on a server or a data center, which will provide high reliability, high availability, persistence, and accessibility through multiple devices. Examples are the VNC, Windows Remote Services, the Citrix Zen Desktop, and other features. Then we have application server virtualization. So this application server virtualization will abstract and consolidate multiple application servers into one server. Thereby, we can use the load balancing strategies here and high availability infrastructure to enable reliable security or service delivery. So this approach will improve the service quality by providing greater scalability and flexibility, which is similar to storage virtualization. Next we have is role of virtualization in cloud computing. So this is again an important topic which could be asked in exam. And this is important from exam perspective. First one we have is execution virtualization. Under this we have two: hardware virtualization and programming language virtualization. Hardware virtualization means it will play a central role in infrastructure as service offerings. For example, it will enable to create virtual machines, share the same physical hardware while running different operating systems in isolation. In programming language virtualization, we are providing the platform as service offering where virtualized environments can run applications which are written in different programming languages. Then we have customization and isolation. So virtualization will provide the sandboxed environment that can be fully controlled. So this is useful for cloud service providers, which will allow them to offer configurable environments that meet specific user requirements within inference between the different users and the workloads which are present there. When we have resource efficiency and server consolidation, that is, we have server consolidation and virtual machine migration. Server consolidation means you are consolidating the workload onto few servers. Thereby, you are maximizing the resource utilization and reducing the cost here. Then we have virtualization, virtual machine migration. It means that the VMs can be migrated from one server to another server. Concept of live migration is seen here. Then we have storage virtualization. So here you make use of the virtual storage services like Google Drive and all of that. Then you have desktop virtualization. It will provide us the remote desktop access. We have discussed here all these topics. Next we have is efficient workload management. So cloud computing supports on-demand scaling where resources like virtual machines can run or stop based on the application requirements. Thereby, it is on-demand scaling is happening here. Next, we will look into the advantages, disadvantages. So the first one is we'll speak about advantages. We have managed execution and isolation. So here virtualization will enable creation of secure isolated environments where other harmful operations can be restricted. So here you have user virtualized environment and the server. So you are making sure that this environment is isolated and it is safeguarded from third party. So this is very important for server consolidation. It will provide better control and security aspect also it is better. Then we have portability, that is virtualized systems like virtualized machine instances can be easily transported as files. So they are self-contained, they'll simplify the administration process. So portability is useful when we are migrating the workloads and managing applications across different hardware systems. Then we have resource efficiency. Resource efficiency means multiple systems can share the same resource or the same hardware without any interference happening. Cost reduction means because you are not making use of any hardware here, separate hardware here, there are few physical systems which are needed to handle the same workload. Virtualization will lower the hardware maintenance and energy cost. Then we have security. A security aspect we have spoken here, right? It will provide sandbox environments, controlled environments, reducing the risk of harmful software. Then we have dynamic resource allocation. As and when there is need, resources are allotted. If not, it is stopped. We have seen in this part, efficient workload management. On-demand scaling is can be written here. Speaking about the disadvantage, first one is performance degradation. So virtualization adds an extra layer between the hardware layer and the guest system. So thereby it can increase the latency and reduce the overall performance. So this is notable in hardware virtualization because the overhead involved in managing the virtual processors, privilege instructions and pagings are pretty evident here. Then we have inefficiency and degraded user experience. Some host features, no, they may not be able to, or they may not be accessible to the virtual machines due to abstraction layer. So again, it could be a disadvantage. Then we have security vulnerabilities. That is, there could be new security risks like malwares that can emulate the virtual environments or any other similar security threats. Then we have complexity in resource management. So by virtualization, it will add complexity to manage the resources, which can sometimes lead in suboptimal resource allocation. So it will further impact the efficiency, performance, and all. So that was about the advantages and disadvantages. Now we have the technology examples. So we have three technologies here: Zen, VMware, and Microsoft Hyper-V. So in exam, definitely one would be asked among these. So either Zen could be asked, or the Hyper-V could be asked, or VMware could be asked also. Let's look into Zen. So Zen Paravirtualization. Zen is an open source virtualization platform which is based on Paravirtualization. It was developed by the students of Cambridge, by University of Cambridge, and it is supported by large community which is called as Citrix, which offers commercial version called Zen Source. So Zen can be used for desktop, server virtualization, and cloud solutions. The core component here is the Zen Hypervisor, which is responsible for managing and controlling the access to hardware resources for virtualization machines. So Zen Paravirtualization will allow for high performance guest operating systems by modifying the parts of guest operating system which will directly interact with the hypervisor. So you are handling the privilege instructions here. So it has better performance by eliminating the performance penalties associated with emulating the privilege instructions in hardware. Here the guest operating system must have hypercalls instead of privilege instructions that would require the kernel mode access. So the Zen hypervisor runs at ring 0 and manages resources such as memory, the CPU, IO resources for guest operating system. Guest operating system runs in the separate domain where the domain 0 has special privileges, manages the virtualization or virtual machine creation, configuration and termination. So if you look at this figure, it speaks about the Zen architecture and the guest operating system management. First one we have is Zen hypervisor here. So Zen hypervisor is called as the virtual machine manager also. So it will run at the highest privilege level, that is the ring 0 or the kernel mode. So it will control and manage the entire virtualization environment. It will directly interact with the hardware, CPU, memory, IO devices, all of that, and it will provide a virtualized environment for the guest operating system. Here the operations are the memory management, CPU state registers and device IO operations to happen. So next, after that we have in domain 0. In domain 0 we have the management domain. So management domain means it is a privileged virtual machine that will manage the Zen hypervisor. So this will manage the Zen hypervisor here and any other guest virtual machines here. So it is the only domain that will have direct access to the hardware resources through the hypervisor. So this domain 0 is typically used for system management tasks, which will include the VM management, VM management means managing the other virtual machines, creating, destroying, configuring, and all of that. Then we have HTTP interface, means we are providing an interface. It could be the web-based API for administrators to interact with the hypervisors and control the VM machines. Then we have access to the hypervisor. That is, you are providing, making the system calls happen to the kernel mode here. Then we have in the domain U, we have user domains. So user domains will represent the unprivileged virtual machines which are running on top of the Xen hypervisor. So here each guest operating system will run its own user domain. So these domains, no, they'll not have direct access to the hardware. Instead, they'll make use of the Xen here. They'll make use of Xen hypervisor through a virtualized interface, and they must make hypercalls here to communicate and perform, or if they require any resources, they can make use of the hypercalls here. So here the functions include guest operating system, that is running the guest operating system, then modified code base, that is if there are any modified versions to run, so we can properly interact with the Xen hypervisor. All that is done using user domains. Then we have hypercalls in Xen VM. So again, as I told, hypercalls are required. Then lastly, we have the privilege rings. So those are ring 0, ring 1, ring 2, and ring 3. In ring 3, we have this is the least privilege, where the user domains will run. So the guest operating the system in these domains will operate with limited privileges, which are relying on the Xen hypervisor to perform privilege operations on their behalf. So that's how this entire figure or the Xen architecture works. So here I have mentioned all the points. Next we have is the VMware full virtualization. In this full virtualization, VMware will replicate the underlying hardware entirely. It will replicate the entire hardware. So here guest operating system will run unmodified, and it is not aware of the virtualization layer which is present there. So it is achieved via binary translation. This is for the sensitive instructions, and direct execution for non-sensitive instructions. Speaking about the hypervisors, there are two types here. One which is directly installed on the hardware, that is type 1, and second one is which will run on top of the existing hardware, that is type 2. Then we have binary translation here, which will translate the sensitive instruction into safe set of instructions. So here we make use of caching to improve the performance by reusing the translated instructions. Along with that, it will allow the virtualization of x86 architecture without any operating systems modification. Speaking about the hardware assisted virtualization, it is introduced with the Intel VT and the AMD V, that is from 2006 onwards. So this will support the direct virtualization of x86 architecture by simplifying the instruction translation process. So here, if you look at the figure, we have a full virtualization reference model. So in this, the third layer, we have the user applications. So these are the applications that will run inside the guest operating system. So that is in the round 3 or the ring 3. So the guest is unaware that it is running in the virtualized environment, meaning that it is of the form that the perspective of applications that they are running on the physical machines. But then in reality, they are not running on physical machines. They are running on the virtualized environment here. Guest operating system. So guest operating system is unmodified. So this will run in the ring 1, and it is not aware of the hypervisor. So here the sensitive instructions like privilege calls are intercepted by the hypervisor directly. Next we have ring 0. So in ring 0 we have hypervisor. So hypervisor operates with the highest priority or highest privilege. It will manage and control the virtual machine execution. It will intercept the instructions from the guest operating system to ensure that virtual machines can run securely and efficiently. It has binary translation and instruction caching, and the sensitive instructions are dealt properly here, or they are dealt directly here. So all the points have been written here. Next we have is the virtual machine VMware workstation architecture. So VMware workstation architecture. Firstly, we have the user applications on top. So user applications will run in both host and guest operating systems. On the host operating system, they will operate in the ring 3, and which are like in ring 3 they'll have restricted access to the hardware resources. In guest operating system also they'll run in ring 3 only. Then coming to host operating system, the host operating system is the operating system which is installed in the physical machine. So it will run on ring 0, that is the privilege mode. So here in the host operating system, it will include a VMware driver. So we have VMware driver here for managing the hardware access. Then we have VMware applications here. So these applications, they'll create and manage the virtual machine instances. So they'll handle the IO requests and perform binary translation when required. After that, we have virtual machine instances, VM instance. So in virtual machine instances, guest operating system will run within the isolated virtual environment. It will support the integration with the host operating system for operations like folder sharing and all of that. Next, we have VMware components and solutions. So first component which we have is end user or desktop virtualization. So here we make use of the VMware workstation, which will create the isolated environment. Then we have VMware Fusion, that is Mac OS, which will virtualize Windows or Linux environment on the Mac OS environment. Then you have server virtualization. We have VMware GSX server, which is an early solution for server virtualization using the remote management capabilities. Then we have VMware ESX or ESXi. So ESX or ESXi features a minimal OS kernel for efficient resource management. It will offer centralized management, resource scheduling, and integration with the network and storage networks. Then we have infrastructure management, infrastructure virtualization. We have VMware vSphere here. So VMware vSphere will combine the virtualized servers into a unified infrastructure. Then we have VMware Cloud, which is an infrastructure as service solution with self-service provision for the virtualized environments. Then we have cloud and application solutions. For example, the vFabric and Zimbra. So vFabric is the scalable Java application, which Java application development on the virtualized infrastructure. Coming to the other one, it is the software as service infrastructure or software as service protocol for email and collaboration, which is fully hosted on the cloud here. Next, moving on further, we have the figure 13.14 and 13.16. So 13.14 is about the VMware GSX server architecture. So this is not that important. And here also VMware Cloud Solution Stack, it is also not that important. You can neglect these two figures. Moving on further, we have the Microsoft Hyper-V. So this is the third technology which is present. So even this could be asked in exam. So Hyper-V is Microsoft's infrastructure virtualization solution for server virtualization, and it will make use of the hypervisor based approach that will support various operating systems. So this Microsoft Hyper-V is integrated as a component of Windows Server 2008 R2. So this is the component or the model which is present where hypervisor is installed as server role. So despite being installed through the operating system, it will directly manage the hardware interactions. It will be like the hybrid solution between the bare metal and the hosted hypervisors. So looking at the architecture of the Hyper-V. So Hyper-V operates by organizing workloads into partitions. So partitions are used for isolating the environments for operating system execution. First one we have is the parent partition or root partition. So this will run on the operating system directly. So it will have direct hardware access, and it will handle the virtualization stack, and it will manage the guest operating system through virtualization infrastructure driver VID, and it will have it will also run the virtual machine worker process, that is PMWP, which will facilitate managing the child partitions by interacting them with hypervisors. Then speaking of child partitions, they will host the guest operating system. So they are again two types. So one is enlightened, other one is unenlightened. Enlightened means it is hypervisor aware. That is, it will benefit from the advanced features like enlightened IO. Whereas speaking of unenlightened partitions, they'll rely on the hardware emulation completely. So next we have the components of hypervisor. So first one is hypercalls interface. So hypercalls interface will provide us an entry point for the partitions to execute on sensitive instructions. So this will support the para virtualization, and it will enable proper communication between the hypervisor and the user to happen. Then we have memory service routines. So memory service routines will control the memory access of partitions. Then we have advanced programmable uh, interrupt controller APIC and synthetic interrupt controllers. So they will handle the interrupts from the hardware and synthetic hardware. It could be from the direct hardware or it could be from the virtual processors. Then you have scheduler, which will allot physical processor time to virtual processors based on the defined policies. Then we have address manager. Address manager will manage the virtual network address. Then it has partition manager. Partition manager will take care of the life cycle of partitions. It could be the creation, destruction, configuration of partitions, and all of that. So next we have is enlightened IO and synthetic devices. So enlightened IO and synthetic devices will optimize the IO operations for hypervisor aware operating systems. So in this we have it will make use of the VM bus, VSBs and VSCs. VM bus will act as the interpartition between the communication channel that is from the parent and the child partition. Whereas the virtual service provider VSP, it will be the kernel level drivers in parent partition that will provide access to the physical hardware for the parent partition. Then we have VSC, virtual service clients. So these are the virtual devices which will run in the child partitions. They'll interact with the VSPs, and then they'll interact with the VM bus. VM bus is common, which will help us to communicate or interact further. Next, we'll speak about the features and observations. So the Windows server will run as the core here initially, firstly. Then here System Center Virtual Machine Manager will manage all the VM operations through the server, through the virtual machine which is provided. Then it will support the hybrid virtualization. That is, it will blend both para-virtualization and the full hardware virtualization. Para-virtualization can be seen in in the parent-child partition model, which resembles to the Zen, and installation within existing operating system aligns to the VMware. So if you compare these two, we can say that same as the Zen's domain model concept, and comparing these two, our Hyper-V is less flexible in hardware or software requirement compared to the Zen and VMware. Requirements are, it will require Windows Server 2008 R2T, and then it should have 64-bit architecture with hardware assisted virtualization and DEP support. So from these we can say that advantages are, it will provide flexibility in order to support multiple hardware or multiple operating systems, and it will be easy to integrate with existing Windows Server environments. But then disadvantages, it is just limited to 64-bit architecture and it requires modern Windows Server platforms. So we can say that Hyper-V provides a robust virtualization platform. It has better flexibility, and it plays a very important role in Microsoft's cloud virtualization strategy. So this was about the second module. I would suggest you to focus on these topics, these three technologies, because the diagrams are slightly trickier and it will take time for you to understand. So cover these three first, and then you can look into the other topics easily. Stay tuned. I'll be uploading the other modules pretty soon. If you have any doubts, do let me know in the comments and subscribe to my channel. Thank you.